In this video, we'll explore another powerful sparse matrix format called the ELL. While CSR is compact and flexible, it can be inefficient on GPUs because different rows have different number of non-zeros, and this could cause a load balancing issue. The ELL format fixes that by making every row the same length, allowing for aligned memory access. So we'll start with our simple 4x4 matrix as we've used in the other examples. Most rows have a different number of non-zeros. This is what we'll work on fixing to improve the load balance. Similar to what we did in CSR, we will extract the non-zero values as well as their column index. So let's label our rows and columns. 0, 1, 2, 3. Similarly, 0, 1, 2, 3. Now let us extract the non-zeros from the first row, as well as its columns. Now we could label these column index and value. We do the same for every other row. Now this still doesn't fix the load balancing issue. As we see, row 1 has more elements than the other rows. So how we fix this is by padding. We pad every row so that they all have the same number of columns as the longest one. If a row has fewer non-zeros, we insert dummy values, which are generally zeros, to keep the structure rectangular. I will include an asterisk to serve as the padding value. Another issue that we experience from CSR is that the memory access isn't coalesced. This makes GPU access inefficient. To bypass this, the ELL format stores data in column major order, meaning that all the first non-zero values from each row come first, and then all the second ones, etc. So it would follow this pattern. Now let's reorganize our ELL format to show how a GPU would access these values in ELL format. So first we have the call index array and the value array. So since we're moving in column major, I'll grab the first column. And I'll do the same for the values. And I just continue until the entire matrix is converted into 1D arrays. Now how this format achieves parallelization is by assigning a thread to each row. in the first iteration, these 4 items will be processed. As you can see, the data is also coalesced, which solves the issue that arises from CSR format. In the second iteration, the threads will move down, and as you could see, there is a more balanced load between iterations until all of the values have been visited. Now, what happens when we add a new value? Well, that depends. Depending on which row an item has been accessed in, will determine what happens. Let's say we insert a 5 into row 3, column 1. When we add a new element, we first check if it fits within the current padded width. Row 3 had previously had 1 non-zero element, which is less than the maximum of 3. So it does fit in the current padded width. So we simply fill the empty slot and record the column index number. So we simply have to find the row this value belongs to and the empty space. The 0th row pertains to the items below 1, 2, 3. 0, 1, 2, 3. 0, 1, 2, 3. Since we found the 3rd row and an empty slot, what we do is we insert the column ID, which in this case is a 1, and we insert the column to be added. But now if an element causes the row to exceed the current width, for example, we add a 3 to row 1, we would need to rebuild the arrays with 1 more column and more padding to accommodate the new maximum. I will leave this as an exercise for you guys to work on. However, as you may have imagined, the more uniform a distribution of non-zeros between rows of the matrix is, the more efficient the ELL format is.